Audio Jungle. Audio Jungle.
All right, so we'll talk about Poisson ratio, right? So Poisson ratio, Poisson's Poisson ratio. All right, now, and it is denoted by mu. In two books, it is denoted by 1 by m. Okay, so mu is equal to 1 by m. In two books, it is denoted by 1 by m. So nothing to worry. We can take any notation. We'll prefer here mu better. Okay, that will be convenient to us to write the equation in this way. So, what is the mean of Poisson ratio? Basically, it is the ratio of the lateral strain and linear strain. Lateral strain and linear strain. That ratio will be called as a Poisson ratio. Be called as a Poisson ratio. Simply, how to understand this? What is the mean of lateral strain? Linear strain, you know very well. Linear strain, you know, but what is the mean of lateral strain? So, just think about it. When a material undergoes a change in length, when a material, it may be rectangular bar, it may be cylindrical bar or anything, but once that material is what, due to force, it is the material undergoes changes in length, then it undergoes change of opposite nature in lateral direction also. Why I said opposite nature? You see the diagram, then you may understand simply. Suppose now we have this bar. Okay, this is the bar now. This is the bar now. Here the length is what, given L. You are applying the load P. You are applying the load. Okay. Now what will happen? It's very clear. Already it is explained. Once you apply the tensile load, because this is the tensile load. So because of the tensile load, this is the actual length. This is the actual length. Lengthwise, it is actual. But because of this tensile load, this bar will be elongated, or the change in length will be there. The change will in length will be there, but it will be in direction of, you can say, x. This is x and this is what, y. But what happens to in y direction? So if this bar is what, elongating in x direction, then in y direction that bar length or bar width will be decreasing. Simple, because this is the y direction. Okay, this is nothing but width. So L, so once L is the length along the load P and B is the width just perpendicular to the load P. So this perpendicular direction, whatever the change in length, called as a lateral change in length. So perpendicular to the acting load, whatever the direction you will take, that direction will be called lateral direction. And along the load, whatever the direction you will consider, it will be linear direction, or you can say longitudinal direction. So two axes we have basically. Along the force, that axis will be longitudinal. Perpendicular to the acting force will be the lateral axis or lateral direction. So I must say here, like whatever the if it is circular bar, or simply this is suppose rectangular bar, I can take no issue. Rectangular bar also we can consider. So here the length, actual length will be increasing, no doubt, because we are having tensile load. So now this length is what, increase something like this. So this will be the change in length. This will be the change in length. Okay. This much you know very well. Last two classes I had explained that change in length. But what about this width? What about this width? Because the length is what, increasing, hence this width is what, decreasing. So now this width will be only this. It becomes B dash. Okay. Because the length is what, increased. So for that reason only, the width will be decreased. So actual width was B. What was the actual width? Actual width was B, and it will looks like this. See, this is the actual width. The actual width. This is the actual width. So this B and this B was same. This is the actual width B in actual. but because length is what increased now, so this width b is what now converted into b dash, means that width is what decreased, now it becomes b dash. So this lateral change, lateral means just perpendicular direction in this way, this is the lateral, see arrow mark I am giving, arrow mark, this is what lateral. So this lateral is nothing but the perpendicular direction. So this direction change will be called as a linear variation. What it is called? Linear variation. Okay. And in this direction, perpendicular direction, in this direction, this type of variation called as a lateral variation. Lateral variation. Very simple. Lateral variation. I hope this one is very clear. So this thing happens to any shape. This thing happens to any shape. I have taken the lateral. So in lateral, I mean, I have taken a rectangular bar. So rectangular bar, it will be something like this. The rectangular, for the circular also. Okay. This is for the square also. Square bar, suppose we have. So this is the actual. Okay. But if you check in lateral direction also, if now I will show you the variation, so that variation will be something like this. Now this bar is what, suppose elongated, it is elongated in this direction because of this load p, suppose it is elongated in delta L this side, this is delta L variation because of this load p. So at the same time this variation will also be there, I mean that you can say width is what decreased now, width is now decreased. So this is the lateral variation. Similarly for the circular shape also, that diameter will change. How that diameter will change? Now this diameter is what reduced. This diameter will be like this. So this diameter is what now reduced. If it is a rectangular bar, so this diameter will be reduced. Suppose actual bar was something like this. This was the black one. This black one was the actual bar. But you have suppose applied the load. This load, if you have applied, then this bar becomes something like this. See? This bar becomes something like the length is what increased that side, but at the same time diameter is what, this diameter is what reduced. This is now d dash. Earlier it was capital D. Earlier it was capital D, but now it becomes d dash. Means diameter is what reduced. Length increased. See what happening here? Length increased, but diameter decreased. No, decreased. So what happening here? What happening? So whatever the length increment, whatever the we have length in increment, okay, the length increment is called as a linear strain. Okay? In length, whatever the change in length, length is what L, the change in length delta L by L. This is what called linear strain. Okay, but diameter decrement, it is circular bar, so diameter decrement we will have, or decrement in diameter. So this will be called as a lateral strain. This is called as a lateral strain. So change in diameter, just like here, change in diameter is what you just say, change in diameter maybe delta D, change in diameter delta D dash, or simple delta D divided by original diameter D. But because it is decreasing, decrement is there, then it is minus. We have increment in length, so this is what plus. Okay, so ultimately hope you understood the definition of the Poisson ratio. So Poisson ratio, if I define the Poisson ratio, so Poisson ratio is nothing but ratio of lateral strain to linear strain. Okay, and it is denoted by mu. So what is the mu? Mu is nothing but lateral strain, divided by linear lateral strain divided by linear strain. Lateral strain divided by linear. Now if you talk about lateral strain, so change in diameter is what? Delta D divided by D, because it is decreasing when linear strain length is what? Increase. Okay, so this is the formula for the Poisson ratio that you need to remember always. The Poisson. So by definition, this is the formula, and theory part I have written here, but explanation nicely here I have explained. So hope you understood about the lateral strain. Okay, generally if you go for the value, okay, if you go for the value, so it's basically, if you talk about the most of metal, okay, most of metal, point number one, most of metal, mu is what? Most of metal mu is what value? 0.25 to 0.33. Okay, but 0.2, especially for steel mu value, this is the MCQ. Mu value is what, for the steel is what? 0.3, Poisson ratio 0.3. And third, for concrete, for concrete for concrete, what is the Poisson ratio? 0.15. So this data you need to remember, sometimes it is required. Okay, this is all about the Poisson ratio. Now coming to the volumetric strain. Till now we had seen the volumetric strain. It is change in volume by the original volume, but to write for the rectangular bar, we have, with length L, width B, and depth is D. Then if you want to write the volumetric strain, then how you would write, that is very important, and we have to see that. So volumetric strain, here I can say volumetric strain. Okay, so now if you talk about the volumetric strain, so when a member is subjected to stress, it undergoes deformation in all directions. Okay, so I must say, I will show the diagram here. Suppose this is the one uh, rectangular bar. See, something like this. This is the one bar. Right. This is the one bar XYZ, and if you check, when this member is what subjected to the different direction, stresses will be there, sigma x, sigma y, sigma z. Okay, so whatever the volumetric strain, that volumetric strain will be in x direction. Suppose here I can give the axis, this is what? X axis. Okay, this is the x axis, y axis, and z axis. We have here x axis, y axis, and z axis. All right, now coming to this, obviously in x direction, what is the strain? X direction strain is what? Epsilon x. In y direction strain is what? Epsilon y. I'm talking about linear strain. In z direction strain is nothing but epsilon z. So if you calculate what is the volumetric strain, so basically the ratio of change in volume to original volume is called volumetric strain. So epsilon b is nothing but, it's a change in volume by original volume. Change in volume by original volume, right? Now, so if any rectangular bar we have here, and we can say this is nothing but length L, this width is nothing but B, and here it is nothing but depth is nothing but, okay, right. Now, so what will be the volume, original volume or simple volume for this? Okay, what is the volume? Length into width into depth, means LED. This is the volume of this bar, right? Volume of this bar. Now if I want to write the change in length, then how you would write? How you would write? So change, this is the volume. Now I can write here V is equal to L D. This is my equation number 1. Second, I just want to write the change in volume. Change in volume. So change in volume means what? Delta V. So we have a V is equal to L BD. Now what is the delta V, which is nothing but change in volume? So delta V is nothing but dV, okay, and this dV is nothing but change in volume. So how to get that change? So make two constant and one variable here. Like I can make BT as a constant, so L will be variable. We can write del L into. Similarly, you can make any two constant like L and D. You can make constant L, and D you can make constant. Then B you will be make variable. So it is dB. Similarly, L and B you can make constant, and you can make right variation of dt, right? Dt or del you can write. It's your choice. So this is the change in volume. Now what is the volumetric strain? Now volumetric strain. So it is denoted by epsilon V. What is that? A change in volume divided by original volume. So what is the epsilon V? Now see what is the change in volume. Just now here you have written it is nothing but delta L dd L dB into D plus LB into L, okay, divide by original volume, which is nothing but you can say it is V. We have to divide by original volume. So obviously it will be divided for all three. Now you can check here uh, delta L we have here, okay, and what is this V? V is nothing but again you can I want to write delta L dd. This volume, what is the value of volume? Volume is nothing but L d. Similarly here L dB into D divided by L dt. Similarly here L d dd divided by what is V? L dt. Now see uh, this is what BD, and this is what DD. Cancel out. This is the you can say L is cancel out, L is cancel out, D is cancel out, D is cancel out. Similarly here we can say L cancel out, L cancel out, D cancel out, B cancel out. What is we have? Delta D by D. So I can write epsilon V is equal to, it is delta L by L plus dB by B, and this is what dd by D. Last you can see. Huh? That also maybe you have confusion. So this delta L you can write in this way, because for D we will have confusion always. So this D you can write delta D by V, and this dd delta D. Now it will be clear. Otherwise you may understand D by D, D into D by D, one D will be cancelled out. It is not like that. It is D for derivative I am saying, okay. This D is derivative actually. So for that D I have converted in delta just for understanding only. This is nothing but epsilon V. Epsilon V. What is delta L by L? If you remember, in L direction, what is the change? What is the strain in L direction? L means x direction. X direction means epsilon x. X is in direction of L. So what is the epsilon x? It is delta L by L. Change in length by original length. That is strain. Similarly, in y direction, what is y? It is B. So B is nothing but del B by V. In D direction, it's Z direction. What is Z? It is epsilon Z. What is the value of epsilon Z? Epsilon means strain. So it is change in length, that is dou D divided by original depth. That is, so if you check, these are the strain epsilon x, epsilon, this is epsilon x, This is epsilon y, and this is what epsilon. So the total change in volume or volumetric strain is nothing but it's a summation of strain in all three direction. In direction of x, what is the strain? In direction of y, what is the strain? In direction of z, what is the strain? You add all, then you will get the volumetric strain. This is the method to calculate that value. Okay, this is for what? This is for the rectangular bar. This is the rectangular plate, or you can say rectangular bar. It's your choice. You can write rectangular bar or rectangular plate. Okay, this is for the rectangular. Here I have right volumetric strain for what? Rectangular bar. Okay, now suppose I am interested in a circular bar also. In circular bar also I just want to check what is the strain. Then what I will do for the circular bar, again it's very simple, but you have to focus, because in examination question they are asking. Okay, so you have to focus here. In case of rectangular bar, it is nothing but you just simple write the formula, so you may understand what is the formula here. Simply see, formula for the rectangular bar is what? You have to write volume, that is area into one side or one length. You have to write, right, area into one length. So what is the area for the circular bar? It is nothing but pi by 4 d square. It is pi by 4 d square. Okay, that will be the area for the circular bar. All right, now I must give the value here directly to you for circular bar. Is sometimes it is required. Okay, so you can use that. This is similarly we have spherical bar, that object also. For that also we can calculate, but here I just want to give the circular bar in simple.
Sir, can you just show the previous slide once again?
So now done.
Yes, sir. Yes, sir.
Okay. So we have circular bar. This circular bar, you can say the length of circular bar is nothing but L, and this circular bar have a obviously a circular cross section. So the length is nothing but L, and obviously it's a circular cross section, so diameter will be there. What is the diameter? Small d. If I say what is the area, so you have to say pi by 4 d square, the area. Now if I say what is the volume of the bar, because we are interested in volumetric strain, so what is the volume of bar? Volume of bar V. It is nothing but area into one length. So pi by 4 d square into length will be the area. Okay, if I say what is the change in volume, how to get change in volume, so I can say delta V, right? So my pi by 4 is what? Constant. I can take common this, then d square we have to differentiate. What is the differentiation of d square? It is 2 d into delta d plus. Okay, this is the differentiation of d square into this second one you have to keep as it is. Then first, again second one you keep, first one you keep as it is d square, and second one you have to differentiate, so it is delta L. Again I will explain you. See, pi by 4 is constant because you are interested in change in volume calculation. So change in volume will be delta V. Pi by 4 take constant. What is the variable? You have diameter and length. So first time you have to differentiate diameter with respect to the diameter only. So it will be d square differentiation is what? 2 into d into dou d. And second variable, which is L, you keep constant as it is. So it is L plus, keep first one as it is d square, and second one you have to differentiate, that will be dou L. Okay, L differentiation with respect to L only. uh, it's a partial derivative basically, so dou L you will write. Okay, this is the delta V. Now if I say what is the volumetric strain for the volumetric strain epsilon V, it is nothing but change in volume, okay, by V, or delta V by V. So what you will have to write? Epsilon V is equal to delta V by V. What is the delta V, it is nothing but pi by 4. You can write the whole bracket value, pi by 4, in bracket we have 2d delta d L plus d square delta L. This is the whole bracket. This is the change in volume divided by original volume. What is the original volume? Pi by 4 d square into L. Check original volume V. Yeah? So see, value will be cancel out, pi by 4 cancel out. What you will have? Epsilon V. In bracket you can check, it is 2d rho dl divided by pi by 4 cancel out, it is d square L plus d square rho L divided by L, d square L, no? D in denominator, because pi by 4 is what cancel out. In denominator what you have only d square L you have. So just segregate this, then what you will get? Check, uh,
Yes, sir.
d this is d into dou d. So 1d will be cancel out, you will have an ll cancel out. What you have? 2 into dou d by plus, see here, d square cancel out. Here you have dou l by l. So ultimately what you got? See, in direction of diameter 1 strain will be there. One strain will be there in direction of diameter. So you have to take, it is nothing but epsilon d. You can write 2 into epsilon d, strain in diameter, plus strain in length, epsilon L. That is nothing but epsilon v. That is the change in, volumetric strain. Epsilon v is nothing but volumetric strain. So basically here it is very clear. One L is what? In direction of xc. For the circular bar, L is what? This L is what? X direction, X. And you can say, because diameter means it's a circular cross section like this. For circular cross section, your y axis and z axis will be same. Okay, so that's the reason here epsilon y and epsilon z will be same, because for the circular cross section, uh, radial direction, all dimension will be same, y and z will be same, hence strain will be same. But along the x length is what there, along the x length is what there, that is totally different from the diameter. Hence in x direction, what is the strain? Epsilon x. But in y and z direction it will be the same. What is that? Epsilon d. Okay, so you, instead of epsilon d, anything you can write. I mean, you just write epsilon d is nothing but epsilon d. You can write epsilon y, or you can write epsilon z. Meaning will be same. There should not be any confusion. So ultimately, epsilon v, which is nothing but volumetric strain, and that is 2 times of the strain in y direction, plus strain in x direction or L direction. You can write the other way also. You can write in few books, you may get volumetric strain is equal to 2 times of the epsilon uh, y plus epsilon x. Okay, this also you can write 2 times of epsilon z plus epsilon x. So x means it is in L direction. Okay, and y and z, I told you it is same. So this formula is what? Volumetric strain for the longitudinal, for the longitudinal, for the circular bar. Okay, for the circular bar. Now here we have to talk next, what we have to talk, that is the elastic constant. Okay, all right. So here in today's session we'll talk about elastic constant. Elastic constants. So basically 3 elastic constants here we are going to discuss. It is nothing but, first one is the modulus of elasticity. Second one is the modulus of rigidity. and the third one is bulk modulus. Okay. Now, if you check this modulus of elasticity, also called Young's modulus, and it is denoted by capital E. It is denoted by capital E. Similarly, modulus of rigidity, it is denoted by capital C, and similarly, bulk modulus, it is denoted by capital A. Right? Anyway, so till now, the Young modulus is what defined once I explained the Hooke's law. So Young modulus, there I had defined what was the Young modulus. It was the basically constant, okay, and that was the ratio of what? Ratio of the stress, okay, the ratio of the direct stress divided by direct strain, or simply you can say stress by strain. All right, so it was E is equal to sigma divided by epsilon. This was explained. This was
Yes, sir.
explained there. Yeah, okay. And up, it is valid up to elastic limit. It was discussed up to elastic limit. This is valid. Okay. Actually, the fundamental Hooke's law, if you see, then stress is what directly proportional to strain. Once you remove the proportionality, then you will get proportionality constant. That is nothing but E, which is nothing but Young modulus. So it was defined nicely. So no need to define here again. Simply another is nothing but modulus of rigidity. Okay? Modulus of rigidity. All right. So modulus of rigidity yet to define. So we can say it is defined as the ratio of shearing stress. Earlier it was direct stress. So here for the modulus of rigidity, it is defined. Okay. It is defined. It is defined as the ratio of as the ratio of shearing stress to shearing strain. So if you check the difference, okay, and this is also within elastic limit as per Hooke's law, within elastic limit. Okay, and it is defined by what? It is defined by capital G. So if you check Young modulus and modulus of rigidity, the formulation will be same. Only in case of Young modulus, stress was direct stress divided by linear strain or direct strain. Similarly here, the modulus of rigidity, it is defined as the ratio of shear stress. It is denoted by G. So it is nothing but ratio of shear stress divided by shear strain. Shear stress, it is defined as a tau, and shear strain is what defined by gamma. Okay, or sometimes it is also defined as a phi. Okay, sometimes also defined as phi. So doesn't matter. I will say standard pattern you have to follow. It is nothing but tau is directly proportional. Shear stress is directly proportional to shear strain. Hence, once you remove the proportionality, you will get the modulus of rigidity, which is constant, and that is denoted by G. So here you will have a tau is equal to G times of gamma. Gamma is nothing but shear strain, and this is this is valid up to elastic limit. Okay, so this is all about the modulus of rigidity. Now third, what we have? Bulk modulus. Okay? Third, we have a bulk modulus. So we'll go for the bulk modulus. and we'll see what is the bulk modulus. So general idea about the volumetric strain I had given already. Okay. So generally, see, now if you check, this is the uh, suppose free surface of the fluid, just for example, free surface of the fluid. Okay, and here one body is what emerged inside the fluid. Okay, one body is what emerged inside the fluid. So what will happen? The force will be applied in all direction perpendicular to this surface. Okay, like this. Uh, if it is what it is fluid, okay, if it is fluid, so force will be applied. Okay, force will be applied by the fluid particles around the surface of the body, and it will be in all direction. No? It will be in all direction, which is nothing but mutually perpendicular. So the same thing, if I will take one component for the structure point of view, so I can say, suppose this is the one body. 3D body I am taking here. So all surface you will able to see. All right. So if the force is what applied, doesn't matter. It can be tensile, it can be compressive. It's your choice. If you take compressive load, then obviously length or dimension will be negative. You have to take means certain. It will try to shrink the body. It will try to shrink the body. The surface will be, shrinking once compressive force is there. But once it is tensile, then elongation in all direction will be there. Okay, that positive and negative both. So I'm considering I can take here tensile force P on this surface. Similarly, we can take tensile force on this surface also, E, and other this surface also we can take tensile load, which is nothing but P. So what will happen in all direction? We have a deformation, elongation, you can say, and strain will get in all direction. So in this situation, if you check what is the bulk modulus, so the bulk modulus is nothing but is the defined as the ratio of the identical pressure or load in three mutually perpendicular direction. Three mutually perpendicular direction means if you see the surface x y z, x y z, so in all direction, like here you can see the faces. So all three faces we will have a load. Okay, we will have a load which is acting perpendicular to the surface. So if you talk about perpendicular to the surface, so as I told you, this can be possible both. This can be a compressive force also, compressive load also. So once you are taking compressive load also, so compressive load is what by nature it's a pressure, because if you check the pressure also on this volume, if you check, it is fluid is what acting the pressure. Pressure will be acting actually because of the fluid. So pressure will be acting around the surface perpendicular. Okay, perpendicular to the surface, pressure will be acting. So similarly, you can take any surface also, and if you are showing on that surface, if you are showing the compressive load like this is the compressive load now. So if you can say it's equivalent to the pressure load also. Pressure load in the sense pressure force divided by area will be the pressure. Yes or no? So both possible. I mean,
Yes, sir.
you can take pressure or you can take load. It's your choice only. The ultimate definition, if you want to write, what is the definition of the bulk modulus? So bulk modulus, you can say, you can write this theory part for this particular. When a body is subjected, when body is subjected to identical pressure, okay, or stress, okay, in three mutually perpendicular in three mutually perpendicular directions, okay. The body the body undergoes uniform changes in three directions in three directions, undergoing distortion of shape, undergoing distortion of the shape, okay. So what is the bulk modulus? So bulk modulus is nothing but it's a ratio it's a ratio of identical pressure, or you can say, right, pressure change divided by volumetric strain is nothing but the bulk modulus, okay. So the bulk modulus is basically defined as the ratio of identical pressure P acting in three mutually perpendicular direction to corresponding volumetric strain, meaning very simple. Suppose load is what acting here. If it is compressive load, so obviously the size will be decreasing. So I can show you, this is the size is what now decreased in all surface, okay. On surface side will be decreased. See, all dimension it is now decreased, okay. So obviously on surface, all surface you will have a change in length, so you will get the volumetric strain. But here it is elongation, so this size is what increase. So I can in show the size is what now increase here, like this, like this you can see everywhere, okay, like this size is what increased because it's a tensile load and this is the compressive load, so size is what decreased. So obviously for the complete surface, if you check, then volumetric strain you will get, because all surfaces, all dimension will be changed as per the load, okay. So all right, now coming to the relationship between the modulus of elasticity and modulus of rigidity. We have to show the relation, okay. We have to write the relation between, now we have to derive this relation between E Young modulus, E and G. What is G? G is modulus of rigidity, right? So E is the Young modulus and G is the modulus of rigidity. Now for this we have to derive the relation. Now see, simple one block I will take. The block is nothing but A, B, C, D, C. This rectangular block we have, because uh, G is the modulus of rigidity, and if you check the definitions of modulus of rigidity required, see, G is nothing but shear stress. So shear stress and shear strain we need to show. I told you shear stress also called a tangential stress. If you remember, shear stress also called tangential stress. In basic lecture only I explained shear stress is also called tangential stress. So means you have to show the force on the surface of the this bar or this rectangular body. We have taken one square element. This is the basically square element, and if you check, this is nothing but A, B, C, D. So this one square element we have, and dimension you can say it is this side it is given because it's a square, so all side must be same. So here you can say this is what A. Okay, so obviously this side will also be A because it's a square elements. Okay, square element A, B, C, D. Now on this square element we have a shear stress. Okay, we have shear stress, and obviously shear stress will be acting on the surface, so this shear stress is what acting on the surface in this way. And why this shear stress you are getting? Because of the tangential stress. When shear stress is what acting here, so shear stress because acting on the top, so on the bottom this will be just opposite. Okay, tau here. Similarly on this surface also you have to show the shear stress, it is tau. Shear stress is what? Tau. So on this opposite surface also we have a tau. So this tau is nothing but, what is the tau? Tau is nothing but pure shear stress. Pure shear stress. Okay, and it is acting on the surface. One shear stress is what acting in this on the surface of the square element ABCD. Then what will happen? You just think what will happen. Obviously the surface uh, will be deformed. Okay, this element ABCD will be deformed, and once it will be deformed, then how it looks like, because you have shown the direction shear stress in this way, so obviously this body will be deformed in this direction. See, in this direction body is what deforming, right? So I can show you like this way. So this C is what now reached at this point. Now this is what this C becomes here, this C dash. Okay, and obviously this B, so I can give another name for this. It is nothing but ABCD. So this one we can say E. Okay, right. Anyway, so once body will be deformed, so body will looks like this. So now, so deformed shape or uh, or you can say uh, distorted shape. So I am writing here deformed shape due to shear stress. What is the deformed shape? What is the deformed shape? It is nothing but A, B, okay, and it becomes C dash. Sorry, it's not A B. It's A E. I have to say A E. Check nicely. You will understand. A E. The deformed shape will be E, A E, then C dash and D. A E, C dash and D. This is the deformed shape. This is nothing but deformed shape. All right. Now, now coming to the point here. Coming to the point, the components, once it is deformed, so you take angle, you can take this angle or you can take this angle, must be same. So this angle will be called as the strain. This angle will be called as a strain, and this strain is nothing but basically shear strain. Why? Because shear stress is acting, hence strain will be shear strain, hence strain will be shear strain. So shear strain you can write gamma or phi, it's your choice, it's your choice. Okay, so now coming to the derivation, full derivation of it. If you check, we have this surface B, and this is what E, and this is D and A. I just want to calculate the shear strain, then what we'll do? So we'll do one thing. We'll use the trigonometric relation. This is what tau. Right? Tau I will write here inside. Tau I will write here, so it will be clear. Or this is now tau. This is now tau. Okay. Okay. So I just want to drop perpendicular line on this AE. So once you draw the perpendicular on AE, this is now perpendicular line. Okay. So perpendicular we have drawn on basically this line, or just parallel to this, or just parallel to this. Just this is nothing but to just in this D to E. Now if you draw the perpendicular on this, if you draw the perpendicular on this, right? So you just say this is nothing but B dash. This is nothing but B dash. Okay. Now, if you want to calculate, because DE is what? What is the DE? DE is nothing but diagonal. If you check, DE is nothing but diagonal. Diagonal. Diagonal of the deformed shape. Diagonal of deformed shape A E C dash D. Okay. For the deformed shape, what is the diagonal? It is DE. So on DE we have drawn one perpendicular, which is nothing but BB dash. Okay. So now we can get the strain in diagonal. What is the strain in diagonal? See nicely, you will understand. Strain in diagonal. What is the strain in diagonal? What is the strain formula? Original, sorry, change in length. What is the strain change in length divided by original length? Original length. What is the change in length? If you see, change in length, if you check, or DE, DE minus DE minus DB dash, DE minus DB dash is the change in length divided by original length. What is the original length? You can say it is DB dash. DB dash is the original length. Okay, because generally if you come to this, if body is not deformed, then diagonal will be dB, but once it is deformed, then we can say it is dB dash. But again, it is not dB dash, it is DE. It means it is elongated. So what is the change in length? Then you can say DE minus dB dash. So DE minus dB dash will be this length, which is showing this length, which is showing the increment or change in length. This length we are talking, this length is nothing but change in length, which is increased actually. Okay, so DE minus dB dash divided by dB dash, this is nothing but strain in diagonal. Okay, strain in diagonal. And if you check what is the strain in diagonal, you got DE minus dB dash divided by dB dash. This also you can say it is nothing but DE minus dB dash becomes EB dash, becomes EB dash, EB dash divided by dB dash, EB dash divided by dB dash. Okay, EB dash divided by dB dash. Okay, and if you check this dB dash, which is nothing but original length, and this original length, if you talk, if the body is what not deformed, then dB dash will be dB only. Okay, this dB dash will be dB only. When the body is not deformed, then what will be the diagonal? Diagonal will be dB only. So dB dash and dB, you can say it is almost same. All right. So you can write in this way. This is number one. Now if you check here, this is the simple trigonometric relation. If you remember, what is that? See, this value is nothing but This value is nothing but EB dash divided by what is the dB? dB is nothing but diagonal. If you remember, it's a simple 9th standard trigonometric. You can say it is A, B, C, D. If you want to calculate this diagonal, so this diagonal will be what? D, dB. So this diagonal is nothing but dB is nothing but it's a any side you can take. It may be AB, okay, because it's a square only. It is happening only in square, so it is AB root 2, or you can say CD root 2, because we have given the dimension, it is A. For the square it is A, all dimension. So if you calculate diagonal of the square, so you know it is nothing but side of root 2, and side of root 2. This is basic math only you had done in your 9th standard. To calculate any square diagonal, then it will be diagonal length is nothing but the length of or side of the side of the square into root 2 will be the diagonal length, that you know, very basic. So this dB is nothing but in this way you can say AB of root 2. AB is the one side of the square, so AB of root 2. This is nothing but diagonal. This is nothing but diagonal. Since the angle of deformation is very small, okay, here, then what we can say, we can write strain in diagonal. Here we can say, since, or next I can write, since angle of deformation is very small, okay, very small, we can assume, because it's a square, so any corner angle if you take, okay, once uh, uh, it is suppose deformed, so we can take one angle. The angle is nothing but, see here, we can take the angle, it is nothing but this one, this part, this angle is nothing but 45 degree, right? You can check, this is the 90 degree, so this will be 45 and this will be 45, okay. So I can write here B dash, no? The angle DE B dash will be 45 degree. For that reason we have drawn the perpendicular here, so that we can analyze the angle. So this is nothing but 45 degree angle, okay. Hence EB dash, what will be the EB dash? If you check now, if you, hence EB dash, what will be the EB dash? Check, if you apply cos 45 in the same triangle, B E B dash, if you apply cos 45, what is the cos 45 here? See, what is the cos 45? So cos 45 is nothing but, see, in this case, cos 45 in this triangle, if you apply, what is the cos 45? It is EB dash divided by EB, right? Simple only. So I can write here cos 40 is nothing but EB dash divided by what is the diagonal? EB dash divided by EB.
Yeah.
Yeah. Okay. So ultimately you will get the value of EB. What is the EB dash now? EB dash, this will be useful. EB dash is nothing but EB cos 45, or you can say EB dash is nothing but EB. What is the cos 45? It is 1 by root. So this is the EB dash. Why it is required? Because here you have to keep the value of EB dash. Okay, you can check here EB dash. Now you can see What is the EB dash here? You just now here you have written it is nothing but EB divided by root 2. It is EB divided by root 2. You have to write this. Okay. EB divided by root 2 divided by EB. So here you can say EB divided by, sorry, this is root 2 also. So it becomes root 2 into root 2 becomes 2. So 2 times of AB. You will have EB upon AB. And 2 times, why? Because root 2 by root 2 into root 2 multiply. Okay. So you will have this value. Now coming to this next step of this, up to this it is clear. Now in strain in diagonal, if you check, what is the strain in diagonal? Strain in diagonal is nothing but strain in diagonal. What you had here, see, strain in diagonal, what you will have, see, this value is nothing but, just now you had written here, it was EB dash divided by AB root 2. So ultimately, if you check, once you keep the value of uh, uh, EB dash, it is nothing but EB by root 2, and this whole value, if you check, it is coming EB divided by 2AB, right? EB divided by 2AB is coming. You just keep here EB divided by 2AB is coming, right? Now this is the one thing. Now also you can see here, because EB 1 by 2, you just take one side, this nothing but EB divided by E. Now check what is EB by AB. What is the EB by AB? This EB by AB, now it will be very clear. EB by AB for this, if I am giving this angle is nothing but phi. I told you this both angle will be the same angle, and this phi is nothing but I had given this. You can take shear strain here. I think somewhere I had mentioned this shear strain also defined phi. Okay, tau gamma
Yeah.
also you can write phi. It's your choice, because we are going to use trigonometric function, so it is necessary to show some angle. Otherwise gamma is enough, shear strain gamma is enough. But why I'm phi I'm showing, you will understand easily. So I'm considering, because this is the angular deformation, this deformation is angular deformation. Now if I check what is the tan phi, we have one complete triangle. Now what is the triangle? You just focus on this, then you will understand. See, this is nothing but A, this is nothing but B, and this is nothing but E. All right. All right. Now coming to this angle, it is, as I said, this is nothing but phi. So if I say what is the tan phi, what will be the length here? Tan phi, because this is the perpendicular. Okay. So tan phi is nothing but EB divided by AB. Okay. So EB by AB is nothing but you got tan phi. Now you can keep here. EB by AB is nothing but 1 by, in bracket you can write tan. You know very well, for very small angle, for very small angle, for very small angle, what you can write, tan phi approximate to phi, that you might know, just like a sin phi approximate
Yeah.
to phi. Yeah. So for very small angle, because what will be the deformation? It is very small actually, shear deformation. So now strain in diagonal you got, ultimately strain in diagonal, ultimately you got, what is that? It's nothing but 1 by 2, 1 by 2, instead of tan phi now you can write phi. This is nothing but strain in diagonal, right? Strain in diagonal. Now if you see there, what is the 1 by 2, what is the phi? Now just go back and check here. So this phi is nothing but, here only you had defined what is the phi? If I see the value of phi, so phi will be nothing but, I can write phi is nothing but tau by g. Okay, so it's your choice. Later on phi you can consider it as a gamma also, that will be simple, because here we are having angular deformation, so it is necessary to take some angle. For that reason I took phi. Okay, so this phi is nothing but, now here you can write tau by g. So okay, right. uh, Ultimately strain in diagonal you got, it is nothing but 1 by 2 tau by z. Okay, now we know that in case of the this square, pure shear tau rise the axial tensile also. So definitely in the diagonal, what diagonal we have here, in the diagonal, see, I'll show you this diagonal. Actual diagonal is what, db. See, this actual one is db. So this diagonal db will also have a, you know, axial elongation. It depends on the load. If see, like for the db, because we have shear stress on the bc surface or ad surface, so at the same moment shear strain will be there, but this will, shear stress will also rise to axial tensile stress. Okay, will also rise to axial tensile stress on diagonal, because see, elongation once load is what acting on the surface bc, so elongation will be there. That's the reason de length you got diagonal, it means tensile load. This diagonal db will also experience the tensile load. For that reason we are getting elongation. uh, Along the diagonal we are getting more length, right? Along the diagonal I'm saying. So it means why the length is what increased, because of the tensile stress. So actually there was the pure shear stress, but because of the pure shear stress, deformation will be there, that is the angular deformation, but at the same time there will be the tensile stress acting on the diagonal. Okay, tensile stress also acting on the diagonal. So because of that we have two stresses, and because of these two stresses, one stress is shear stress and another stress we are having a tensile stress. Because of these two stresses we'll get two strain. What is first strain? That is shear strain, that we already have written here. What is the another? Another will be the strain due to the tensile stress, that is the linear strain in diagonal. I hope you understood. So basically two stress will be uh, uh, here acting here. So I will write in single line the pure shear stress, pure shear stress, pure shear stress also rise to axial tensile stress in the diagonal. If you write this line, then you will understand. Okay, in the diagonal. Okay, so now for that tensile stress along the diagonal we have to write. Okay, and this is nothing but along the stress in the diagonal. Okay, direction of db, because what is the diagonal we have here, db. Okay, diagonal is what, db. So in the direction of db, and 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 axial compressive stress perpendicular to it, perpendicular to it. Very simple. If you just see one more time, I will try to explain. See, you just feel, you will understand. Once deformation will happening because of the shear stress, so along the db along the dB, that is the diagonal along the dB length is what increased, so it becomes dE now, it becomes dE now. So here you got the elongation. So elongation you are getting means tensile stress. But now perpendicular, because how many diagonals in a square? Two diagonals. If you check the actual square ABCD, so one diagonal is dB, another diagonal is what? AC. But once shear stress is acting, so along the dB diagonal we are getting elongation, so we can say tensile load. But another diagonal, that is AC, another diagonal, that is AC, and now this becomes AC dash. So this AC dash, if you check the length, it is decreased, it is decreased. If you check the length here, if you check the AC length, now AC length is what? Decreased. See, AC length is what? Decreased. It becomes AC dash, means the length becomes shorter. If length becomes shorter, it means compressive load is what acting. So two diagonals are there. You just try to understand. Two diagonals are there. That is BD or DB, you can say. So along DB we have elongation. That's the reason we are getting DE. But what about another diagonal AC? AC diagonal becomes AC dash, means it becomes shorter. Once it is shorting the length, it means the compressive load will be acting. For that reason, I am giving the statement here. Along the dB we are getting the tensile stress. Along the dB diagonal we are getting the tensile stress along the dB diagonal. But compressive stress will have perpendicular to it, means along the AC. Along the AC will have compressive stress. For that reason, your AC becomes AC dash if you check in the diagram, and dB becomes dB dash. Okay, so here obviously this length is what? Negative, it is shortening the length, and this length is what? Increasing, becomes positive. So obviously here we have a compressive stress C, and here we'll have a tensile stress Ty, because length is what? Increasing. I hope this one is clear now. So tensile strain, now along the diagonal we have to write. So what is the tensile strain? Now almost done. Tensile strain, or you can say, or linear strain along diagonal. So this will be the stress which is acting E. Okay, the stress which is acting E. uh, and what is the stress I have written here? Tau. Sorry, this is stress I have shown tau, right? Tau. It's a tau one. So tau stress I have to write here tau, not sigma, tau. So this is the tau by E. Okay, tau by E. And because two stresses we have here, one is on diagonal dB, uh, because it's a 2D diagram, so two stress will be acting. So one is what? Linear, another is what? Transverse, lateral strain, because we are writing strain, so total strain will be the linear strain, and then plus transverse strain also we have to write. So for transverse strain we have to use the Poisson ratio tau by E. Okay. So you will get the tau by E in bracket 1 plus mu. Okay, now, so what, this is the equation number 2. And what is the diagonal strain? Another diagonal strain, this is the strain in diagonal, this is the equation number 1. Now, so whatever the strain we are getting here, in both cases, this was the strain we got because of the shear stress consideration. We had taken the shear strain. See, shear strain here, strain in diagonal we have written here. See, shear strain, right? Strain in diagonal, that is change in length divided by original length. And now we have used the angular deformation, and finally we got the strain in diagonal. It is 1 by 2 phi or 1 by 2 tau by z, right? But again we have taken the tensile strain in the diagonal, so along the diagonal, then we got these two equations. But in both way our value of strain must be same, hence equation 1 is equal to equation 2. I can write here if you want. Strain must be must be same along diagonal. So from first equation, what you got? 1 by 2 tau by t, and from second equation, what you got? Tau by e in bracket 1 plus. If you check tau tau cancel out, what you will get? You get E is equal to 2 times of g 1 plus mu. See, because this tau tau will be cancel out, right? Tau tau will be cancel out here. So ultimately you will get this. Now this is the relation between what? This is the relation between the Young modulus E and G.